Okay, let's go over your practice problems. So in number 1, this is just a really good review of finding components and then to find magnitude and direction. So in D, for vector D, you're given the x and y component. So you're going to use, to find the magnitude, the length of it, you're going to use x squared plus y squared equals r squared. And so if you use that, and here's a couple notes, you know, when you plug in that negative 250, make sure that when you square it, it's a positive number. So make sure you're using parentheses, or just don't put the negative in there, because negative 250 squared and positive 250 squared are the same number. So you should be getting a square root of 559 newtons. And then we're going to use tan negative 1, or arctan of y over x is equal to our angle. Now, I drew a picture of that angle here. Yep. And our vector has a positive x and a negative y. So our vector is right here. And the angle that we're finding when we find tan is that little angle south of the east axis. I want it as a polar heading. So looking at my positive and negative coordinates there for x and y, it puts it in the fourth quadrant. And the rule is when it's in the fourth quadrant, you take the angle off of 360. So when I found the angle, using tan, and then I just took it off of 360, and it gave me 333 degrees. So that's how I got that angle. In I, you're going to use x equals r cosine theta and y equals r sine theta. Be careful. Make sure your calculator is in degree mode. And if you use that polar angle, then you don't have to think about what quadrant you're in and whether or not it should be positive x's or negative x's, or positive y's and negative y's. So that's why I like the polar, because when I take r cosine of 240, it's going to give me a negative 113, and I don't have to stop and think, oh, is this south of west? Okay, I need to, make sure it's west, negative 113, and south, negative 195. All right, so originally a plane is trying to go north, but there's a wind blowing it to the east, to the west, this way. And it's going to blow it off course. So just common sense tells me that if I want to go straight north, then I'm going to have to angle it this direction. So that's what I've drawn here. I've drawn you going this direction and the westward wind pushing you this way, making you go straight forward. And I don't like this because you notice the angle here is across from the x, not across from y. So I drew a parallelogram and redrew in my x and my y here. And what I see is that now 300 is on the y-axis, is opposite this angle here. And that's going to give me the right polar heading relative to the positive x-axis. So I'm going to head somewhere north of east, right, in that first quadrant. So I'm just going to use Pythagorean theorem to find the magnitude, which is 300 squared plus 10 squared, take the square root, which is just 300. It just rounds to 300. And then I'm going to find the angle, 300 divided by 10, take the inverse tan of it. I don't have to do anything because this is in the first quadrant. This is the polar angle. So I have to take a heading of 300 meters per second at 88 degrees to ensure that that wind does not blow me off course. All right, in number 3, you have a dog that walks north, and then he walks east, and then he walks south. So in effect, he's 60 meters east of where he started and 100 minus 20 or 80 meters south of where he started. So my x is 60 and my y is 80 or negative 80. And so I'm just going to use r squared. And once again, I didn't put my negative in here because if I did, I would have to put it in parentheses to make sure that it stays a positive number when I square it. So I just dropped that negative, but because Negative 80 squared is the same thing as positive 80 squared. And I got 100 meters as my value. And this is in the fourth quadrant. So once again, I've got to subtract this value. When I use tan -1 of y over x, I get 53 degrees, but it's in the fourth quadrant. So I need to subtract it off at 360. And that gives me a net displacement of 100 meters at 307 degrees where I started. In number 4, you're going to add vectors. You're going to add multiple vectors that are not at right angles to each other. And the way to do that is by finding all the x components and all the y components and adding them up to find the x and the y component of the resultant. And then using Pythagorean theorem and tan theta to find the direction. And when I did this, I just used r cosine theta and r sine theta. So 200 times the cosine of 180, 200 times the sine of 180, 100 times the cosine of 45, 100 times the sine of 45, and so forth. Now, I want to just make sure that you understand that this is in degree mode in your calculator. So if you didn't do that, you may have gotten radians, and that would be wrong. So make sure you're in degree mode. And I found my net resultant to be negative 208.3 newtons and my net y component to be positive 220.7. And so what quadrant is that in? Well, if it's a negative x and a positive y, it's in, I did that wrong in the example. So let's just go through here. It's over here in the second quadrant. So the rule is if it's in the second quadrant, you take it off of 180, right? Because it's this here and you want this, and what you're finding is this. So you want this big angle. So you've got to take it off 180. So when I do that, it's going to be 180 minus 46.7. And once again, I'm just using tan theta y over x. And I don't even put in the negatives when I do that, when I take tan, because I know I'm going to have to adjust for it myself. So 180 minus 46.7 is 133 degrees. So this has a heading of 133 degrees, and it's a total force of 303 newtons. All right, projectiles. So we first start out with a review of just something that's tossed straight up. So it only has a vertical component. So if I draw the trajectory, when I say trajectory, I just need to see the path of it going up and down, and I want you to label with vectors. Its initial velocity is 50 meters per second upward. It has no velocity at the top, and then at the bottom, it has a negative velocity of negative 50 meters per second. So when I figure out how high it goes, I know VI is 50, and I just want to evaluate it to the top. So I'm just going to go from 50 meters per second to 0. And I always know that gravity is negative 9.8. So the formula I use for that is VF squared equals VI squared plus 2GY. I subtract VI from both sides, and I divide both sides by 2G, and I get 0 squared minus 50 squared all over 2 times negative 9.8. And I should be getting a height of 128 meters. And in C, I want to know how long it's in the air. So now I want to know from when it leaves to right before it lands. So I'm going to use VI is 50, VF is negative 50, gravity is negative 9.8. The formula and I'm looking for time. So that formula would be VF equals VI plus GT. And if you're having problems picking out formulas, you need a formula that has these values in it. That's why it's so important for you to list what you're doing to pick out your formula. So T is going to be VF minus VI all over G, or 10.2 seconds. So notice that it's important to put that negative in for VF. It's negative 50 minus positive 50, which is going to be negative 100 divided by negative 9.8. Now we're going to compare that to projectiles that are thrown at an angle. So now I'm going to throw something up at an angle of 50 degrees. So I'm throwing it 50 meters per second at an angle of 30 degrees, sorry. So it has an x component of 50 times cosine of 30, which is 43.3 meters per second. And it has an initial y of 25 meters per second. So it's going to be thrown up at 25 meters per second. So it's like I threw it up at 25 meters per second, and I threw it forward at 43 meters per second. The 25 meters per second starts to zero. It goes to zero at the top, but the 43 stays the same because there's no force or acceleration in the x direction. So at the top, it has an x velocity of 43.3 meters per second and a y velocity of zero. And at the bottom, it's still moving forward with Vx equal to 43.3 meters per second. But now it's got, right before it hits the ground, assuming it's at the same level, it has a speed of negative 25 meters per second. So when I'm asked about the acceleration in the x direction, there is no acceleration in the x direction. It stays, it's constant speed. And the acceleration in the y direction, if we are assuming that there's nothing but gravity acting on it, so it is negative 9.8 meters per second squared. So when I find how high it goes, I need to use my y velocities, right? Because that's what's going to determine how high it goes. So a big mistake is that people either plug in 50 meters per second. That's not the velocity that stops at the top. Okay. The velocity that stops at the top is 25 meters per second. The y velocities are the ones that are slowing down by 9.8 meters per second every second, not the 50, not the 43.3. So when I find it, I'm going to find it just like I did in the other problem, but I'm going to use 0 squared minus 25 squared all over 2 times negative 9.8, and I get 31.9 meters. When I find the time, I'm going to find the time just like I found in the other problem, but I'm going to use negative 25 as my final speed and positive 25 as my initial speed. And when I do that, I get 5.10 seconds. And then this new question here in G is what is its range? Its range is how far it travels in the x direction. So that is only determined by 43.3 meters per second. It's going 43.3 meters every second for 5.10. So it's just x equals vx times t, 43.3 times 5.1, or 221 meters. And in 7, you're going to have a 200 meter building, and it's going to land 100 meters away. So let's just talk about this. So we've got a building here. This is 200 meters. And so it's falling 200 meters, and it's going to land 100 meters away. So we want to know how long it's in the air. So the thing that determines how long it's in the air is its height. So it's thrown horizontally, so it only has a Vx to start with. So it's Vi in the x direction is 0, y is negative 200 meters, g is always negative 9.8 meters per second squared, and we're going to be looking for time. The formula that has VI, Y, G, and T is Y equals VIT plus 1/2 GT squared. But VI is 0, so this just goes to Y equals 1/2 of negative 9.8 times time squared, and that's equal to negative 200 meters. Now, notice that if you don't put the negative 200, you're going to end up dividing by a negative 9.8, and that's going to give you a negative number that you can't take the square root of. So when I do my math here, I'm going to have t squared equals 2 times negative 200 divided by negative 9.8, and then I'm going to find the square root of all that. Two times 200 divided by 9.8, the negatives cancel out, and I take the square root of that, and I get 6.39 seconds. And then it wants to know the vertical component of its velocity just before it hits the ground. So as it falls, it's going to have a vertical component. It started out with an initial Vy of 0, and then we're looking for its final Vy. So when we find this one, we know that Vi is 0, Vf is what we're looking for. Gravity is negative 9.8 meters per second squared. We could use our time, but if we were wrong, we're going to get this wrong too. So the other thing I know is that it fell negative 200 meters. So we're going to use Vf squared equals Vi squared plus 2Gy. Vf squared equals Vi is 0. So 2 times negative 9.8 times negative 200. Once again, if you forget one of your negatives, you can't take the square root of a negative. So 2 times 9.8 times 200, and then I take the inverse square root of it, and I get plus or minus 62.6. Since it's falling, it's going to be negative 62.6 meters per second. And then what is the velocity of the ball just before it hits the ground? So just before it hits the ground, it was moving forward at a velocity and it was moving downward at a velocity. So let's talk about that. So it was in the air for 6.39 seconds. So let's write this down. It was in the air for 6.39 seconds, and it had a final Vy of negative 62. Sorry, I'm old. Can't remember things. Negative 62.6 meters per second. The other thing we know is that when it landed 100 meters away. So in order to find, so let's just talk about that velocity. We know this component of the velocity, we just found it. It's negative 62. We need to know this component of the velocity so that we can find the velocity it actually hits the ground with, right? This is what we're looking for here. We need to know the x component. We know the y component is negative 62.6. Vx is going to be the range divided by the time, and it went 100 meters in 6.39 seconds. So it has a Vx of 15.6 meters per second. So this is 15.6 meters per second. And this is 62.6 meters per second. So if I want to know V, it's going to be the square root of 15.6 squared plus negative 62.6 squared. I'm just going to plug that in as a positive 62.6 squared plus 15.6 squared. And then I take the inverse of that, and it's 64.5 meters per second. I could take this one step further and give the direction of this if I want to. The direction would be negative 1, tan negative 1 of 62.6 divided by 15.6. I could put the negative in there if I want to, but I know that it's down in the fourth quadrant. And I'm just going to describe this as south of east or below the ground, just for argument's sake. So 62.6 divided by 15.6, and take the inverse tan of it, and I'm getting an angle of 76 degrees below the ground.